Good day, everyone. So for today's topic, we will discuss about surface tension. Surface tension is the attractive force exerted upon the surface molecules of a liquid by the molecules beneath that tends to draw the surface molecules into the bulk of the liquid and makes the liquid assume the shape having the least surface area. Or by other definition, so surface tension is the property of a liquid surface displayed by its acting as if it were a stretched elastic membrane. It is the reason why some insects and needles even denser than water will float on a water surface. This happens because water molecules at the surface of the water are strongly attracted to each other, more than they are attracted to the air molecules above them. Because of this, the intermolecular force is stronger on the water surface than the bottom part of the water. It would take a force of 72 dynes to break a surface film of water 1 centimeter long at 25 degrees Celsius. Because of surface tension, you can tell when your floor needs waxing. Water droplets tend to appear somewhat flattened out. After waxing, you get a nice beading effect. Let's take a look at this figure. So in letter A, this is an example of a weighted surface. So that means that the angle is less than 90 degrees. So that is theta is less than 90 degrees. So that is the case before we put or we wax the floor. And in figure B, that is an example of a non-weighted surface. So the theta or the angle is greater than 90 degrees. This is what happened after waxing the floor. In engineering, probably the most important effect of surface tension is the creation of a curved meniscus that appears in manometers or barometers, leading to a capillary rise or depression, and that is called capillary effect. Okay, so we have an example problem here for surface tension. Okay, so we have the problem: create a graph showing the capillary rise or fall of a column of water or mercury, respectively. As a function of tube diameter d, find the minimum diameter of its column required so that the height of the magnitude will be less than mm. So we have the given tube depth in liquid. Then find, so when we say tube depth in liquid, so this is the tube, so this is the liquid, so this is the meniscus region, and this is delta H. So the difference in the elevation, so inside the tube and outside the tube. Then find a general expression for delta H. General expression for delta H as a function of the tube diameter d. Function of tube diameter d. Okay, Then we have the solution. So we will erase this first. So we have the solution. Okay, apply free body diagram analysis and some vertical forces. So the governing equation. Okay, so the summation of forces vertical, or summation of Fz. So this is Z. So summation of vertical forces is equal to 0. Okay, so this is the figure. The tube. This is the liquid outside the tube. This is the liquid inside the tube. So this is the delta H, and okay, so the liquid is going downward, so because of the gravity. Okay, so we have assumptions. So we will assume that so we will assume to measure the height, so at the center of the meniscus. So this is the part. So we will measure the middle of the meniscus. Measure to middle of meniscus. And number 2, neglect the volume in the meniscus region. So this is the volume of the meniscus region. So we will neglect this. Okay, so we will just measure at the center. Okay, so summing forces in the Z direction, or in the vertical direction. So summing so we have summation of force vertical, so is equal to sigma pi d cosine theta minus rho g, the change in the volume is equal to 0. Rho g d cosine theta minus rho g v. So this sigma right here is the surface tension. So this is the value of the surface tension of the liquid. This pi d here is the perimeter. So this is the perimeter, or the circumference, no, the circumference inside the tube. So d is the diameter inside the tube. Then theta, so this is the theta. So this is the angle inside the tube, the angle due to the surface tension. And rho, so rho is density. G is the gravitational acceleration. And delta V is the volume, no, the change in volume, or the volume inside the tube. So the total volume. So for example, this is the level of the water. So this volume right here is the V, or the delta V. So we'll have delta V. So the volume inside the tube is equal to pi times the diameter inside the tube squared divided by 4. So that this is the cross-sectional area times the difference in elevation, or the height, so at the center. So we will assume or neglect the meniscus region, or the volume of the meniscus region. Then we have, so from the general equation, or the summation of forces, so we have sigma pi d cos theta, sigma pi d cos theta is equal to rho g delta v. So rho g, So this delta B is equal to pi d squared delta H divided by 4. So pi cancel, d squared, so cancel d. Then we have the delta H. Okay, so delta H is equal to 4 sigma cosine theta divided by rho GD. Okay, so this is the capillary rise or fall, or the change in the height with respect to the, so this is the capillary rise or fall, or the change in the height with respect to the, or as a function of the diameter d. So d. Okay, so we now have the relation between the change in the elevation with respect to the diameter. So that is the diameter inside the tube. So this is delta H is equal to 4 sigma cosine theta divided by rho GD. So for water, so we will check on the table. So the value of water is, or the value of the surface tension of water, sigma is equal to 72.8 millinewton per meter. So at an angle, so the theta, so the surface tension angle is equal to 0 degrees. And for mercury, so the sigma is equal to 484 millinewton per meter, and the angle theta is equal to 140 degrees. So for, okay, so creating a graph. So the y-axis is for the capillary height. So this is in mm. And for the x-axis, we have the diameter d in mm. So this is the capillary effect and small tube. So this graph. Okay, so using the relation delta H is equal to 4 sigma cos theta divided by rho GD. Okay, so we'll now create a graph. So to see the relation between the capillary height and the diameter d. So that is, this is the capillary effect and small tubes. So we will use the relation delta H is equal to 4 sigma cosine theta divided by rho GD. So we will solve, or we will graph first the water. So the sigma for water is 72.8 millinewton per meter. Okay, so we will just use calculator. So 4 times 72.8, so this is in millinewton per meter, so we will convert that into newton per meter. So we will multiply it by times 10 to the negative 3 times the cosine 0, so 0 is 4, or the angle of water. Then we have the density rho, so the density is 9 point, below. So density is 1000 kilogram per cubic meter. So times the gravitational acceleration 9.81 meter per second squared multiplied by, so we will assume first the diameter, so we'll use 5 mm. So using 5 mm, D1 is 5 mm. So 5 times 10 to the negative 3. So we will convert this mm into meter. So is equal to, so 5.936 times 10 to the negative 3. So that is 5.936 times 10 to the negative 3 meter. So we will convert that into millimeter. So 5.936 mm. Okay, the answer is 5.936 mm. So 5, 10, 15, 20, 25, 30. So if we'll graph, so the height is 5.936 for the diameter 5. So here, how about if we will use the diameter 2.5? Okay, so we'll substitute the diameter here. So we'll use 2.5. So the answer will be 11.8 or 11.9 mm. So 11.9 mm. So here. Okay, so how about if we will use 1 mm for the diameter? So the answer will be 30 mm. So that is the elevation. Then for the 3 is 10 mm. So what will be the answer for 10 mm? Okay, so we will have 3 or 2.97. 2.97. So for 10 mm diameter, or almost 3 for D4. So for we will use 20 mm diameter. Okay, so the elevation will be 1.5. So 1.5. So here, so if we are going to graph this, so this is the graph of the water. Okay, so this is for water. Then how about for the mercury? So for the mercury, so the sigma is 484 millinewton per meter, and the angle theta is equal to 140 degrees. Okay, so we got this from the table. So these values, so we will substitute this to solve for the mercury. So the for diameter 1, 5, diameter 1, so we will use just 1 mm for diameter 1. For D2, 5 mm. For D3, 10 mm. For D4, we will use 20 mm. Okay, so what will be the elevation for each diameter? Okay, so that the elevation one is, so substitute 4 times the sigma, 484. So we'll convert this into Newton per meter. So 484 times 10 to the negative 3 times cosine theta. So the theta is 140 degrees divided by Rho, the density of mercury is 13.6 times 10 to the power of 3. So 13.6 times 10 to the power of 3 kilogram per cubic meter. So times 10 to the power of 3 times 9.81 times the diameter. So we will use 1 mm. So 1 times 10 to the negative 3. So we'll convert that into meter. So the answer will be negative 0. So negative 0.111. So this is in meter. So if we are going to convert this into mm, so we'll have negative 11.1. So this is negative 5, negative 10. So here. So this is the for 1 the location, no? This is the location or the value of the diameter or the height with respect to the diameter. So for 5 mm, so we'll just substitute the diameter by 5. So the answer will be negative 2.22. So negative 2.22 for 5. Then for 10, okay, substitute 10. So negative 1.11. Then for 20, so negative 5.55 times 10 to the negative 4 or 0.5 mm. So here, so this is the graph of mercury. So mercury, okay, so for the second problem, find the minimum diameter of each column required so that the height magnitude will be less than 1 mm. So we will substitute the height 1 mm. So we will find the value of the diameter. So this is for water. Okay. So D here, so D is equal to 4 sigma cosine theta divided by rho G delta H. So 4 times 72.8 times 10 to the negative 3 times cosine theta divided by 1000 times 9.81 times 1 mm. So 1 times 10 to the negative 3 mm is equal to, so 2.97 29.7, no, 0.02968 meters or 29.7 mm. So this is the diameter of the water for the height, for height less than 1 mm. Then the diameter of the mercury for delta H less than mm. So we will have 4 times the sigma or the surface tension value of mercury 484 times cosine 140 degrees divided by 13,600. So the density of mercury times 9.81 times the diameter the diameter, the elevation or the delta H 1 mm, 1 times 10 to the negative 3 is equal to, so negative 11.11. So is this right? So we forgot to write times 10 to the negative 3. So we forgot to convert into Newton per meter. So we will multiply times 10 to the negative 3 in the numerator. So the value will be 11.1 mm. So 11.1 mm. So that is the minimum diameter for mercury, so that the height will be less than 1 mm. Okay, so that's all for today, and good day everyone. God bless.